Welcome back to lecture number 4. Last time I talked about transfers on the equivariant homotopy groups of orthogonal G spectra. So I discussed different flavors. First I discussed the dimension shifting transfer, where there is a twist in the source by the so-called tangent representation. In this whole context, G is a compact Lie group and H is a closed subgroup of G, and this tangent representation was the tangent space of the preferred coset in G mod H, which naturally comes with a linear H action. More important for us is the degree 0 transfer, or simply the transfer that I've written down here. So this is a map from, say, the 0th H equivariant homotopy group of an orthogonal G spectrum to the G equivariant homotopy group in the same dimension. The connection between the two is that the degree 0 transfer is just you first include here via the fixed point 0 at infinity into SL, and then you follow with a degree shifting transfer. I've also explained some of the most important properties of the transfers last time. In particular, I showed in which sense the transfers are transitive and in which sense they commute with inflation homomorphisms. The transfer also interact in a well-established way with restrictions to subgroups, but that's a little bit more complicated. And today I want to devote the lecture to giving examples and special cases and consequences of this interaction, which is usually called the double coset formula. So here I've written up the double coset formula one more time. The context is some ambient compact Lie group G and two closed subgroups K and H that don't have anything to do with each other. And we also have an orthogonal G spectrum X. And then there's this formula that explains what happens if you first transfer from H to G and then restrict from G to H. As I explained in detail last time, you can rewrite this composite as a sum of terms. So this sum is indexed first of all by conjugacy classes of subgroups of K. And then whenever you have fixed one such conjugacy class of subgroup, you can look at this so-called orbit type manifold K mod H conjugacy class of L. So these are all those cosets, K, G, and G mod H, with the property that the stabilizer, with respect to the K action, is in the conjugacy class of L. So if you spell this all out, this really means concretely that K intersected GH, which is the stabilizer of this element, intersected with K. This is in the K conjugacy class of L. So this is a K invariant subspace, locally closed, and we can look at its quotient space. So we divide out the left K action on G mod H L. So this will be a smooth manifold, typically not compact, and it will decompose into different connected components. And the sum is indexed first of all by these conjugacy classes L, and then by connected components M inside of L, and then this element little g is any element such that K, GH is contained in this connected component M. This number is the so-called internal Euler characteristic, and it's an integer. This sum is finite. First of all, this set will be empty for almost all conjugacy classes L, and then this will always only have finitely many path components, so this is a finite and well-determined sum. As I said, today I want to go through some consequences and special cases and give some explicit examples so that you can familiarize yourself with this double coset formula. This is at the same time a little bit complicated, but it's also of fundamental importance for calculations. Before I start with some examples, I want to remind you of one special feature that happens with respect to these conjugation homomorphisms that come here whenever we have a global homotopy type, because this is something that works for orthogonal G spectra. Later we will mostly be interested in global homotopy types. So that means that the group G acts trivially and then some special things happen. And this is what I want to explain now. So, as usual, we let H be a closed subgroup of G. And then we look at an element G in the normalizer and GH. So these are all the elements such that GH, G inverse is H, so that conjugate the group into itself. So in this situation, the conjugation homomorphism CG goes from H So usually it would go, or always it goes to the conjugate subgroup, but in this situation that's H itself, so it's a self-map of this. And then the conjugation homomorphism for which I always write G lower star. This was the composite. First you do the conjugation homomorphism CG upper star, and then you do the effect of left translation by the element G on homotopy groups. In this situation, if G normalizes H, this is the self-map of the equivariant homotopy groups. H equivariant homotopy groups of X. So moreover, if the element happens to be in H, then this is the identity. That's a little lemma that I mentioned earlier. Then G lower star is the identity. So if you combine these two facts, this means that the quotient group, which is often called the Weyl group, WGH, so the normalizer of H divided by H, which is the quotient group, this acts on the zeroth H equivariant homotopy groups of X. And for a general orthogonal G spectrum, this is the structure that you have, and it doesn't simplify any further than this. But now suppose we have a global homotopy type, let X be a global homotopy type. And I'll use this as sort of informal jargon for the fact that it's an orthogonal spectrum with trivial G action. And then something special happens. So suppose we have an element G, which is not just in the normalizer, but actually in the centralizer. Suppose that G belongs to the centralizer in G of H. So these are all elements, G and G, that conjugate the elements of H pointwise. So G, H, G inverse is H for all H in H. So this is a subgroup, a normal subgroup of the normalizer. And then something special happens. So first of all, because it centralizes, the conjugation homomorphism is then the identity from H to H. So that means CG upper star is the restriction along the identity, so that's the identity. But also LG is the identity from X to X, and this is where we're using that we have a global homotopy type, because that means all elements, in particular this element little g, act like the identity on X. And that means this G lower star is the identity composed with the identity, so we conclude that G lower star is the identity. So this is special. If we have a global homotopy type, this relation does not in general hold if you just have an orthogonal G spectrum with some arbitrary action. So equivalently, you could say that the action of the Weyl group of WGH on pi 0 H equivariant of X factors through the quotient group where you take the normalizer GH and you divide out not just H but also the centralizer G and H. So this is also a normal subgroup that you can divide out. And so there are further relations that happen in the global homotopy type. So a different way to express this is that if you have an orthogonal G spectrum, then the conjugation map really depends on the element that conjugates. Whereas if you have a global homotopy type, it only depends on the conjugation homomorphism, and it doesn't remember which element you conjugated with, only with the effect of the conjugation homomorphism. So this is something we'll want to keep in mind, because then sometimes in the double coset formula, the G lower star will simplify to something. And we'll have an example right on the next whiteboard. The extra global relation satisfied by the conjugation homomorphism is most drastically seen in the extreme case, namely when H is just a trivial subgroup of G. So in this situation, the normalizer of G in G of the trivial subgroup is of course everything, and that's also the centralizer, G of the trivial, because every element commutes with the identity element. So for global X, we have that G lower star, no matter which element G you take, as a self-map of the non-equivariant homotopy groups of X is the identity. So this is non-equivariant is the identity for all G. And this is far from true in general if you have an orthogonal G spectrum, so there you would still have a G action in its role as the Weyl group of the trivial group. G would still act on the non-equivariant homotopy groups. If you come from something global, this action is always trivial, so this is a drastic simplification sometimes. Okay, so now I will do one special case of the double cosets formula that's useful to know. So, special case of the double coset formula. And that's the case where one of the two subgroups, the one that we're restricting down to, is the identity subgroup. So we want to have the explicit formula for first transferring from some arbitrary h to g, and then going down to the trivial subgroup. So in this situation, there's no k action. K is the trivial group. So G mod H is a smooth closed manifold. There's only one conjugacy class of subgroup of the trivial group. So there's only one of these groups that were called L earlier. It's the trivial one, and hence the connected components that we have to consider are the connected components just of G mod H. So the sum will now run over connected components in the homogeneous space G mod H. Then we have the usual formula. So we have the restriction from H. Well, now we would have to go down to K, which is the trivial subgroup, intersected with H. So this would be the trivial subgroup, and then we'll have G lower star. And then we would have to usually transfer up, but there's no transferring up because we go to the trivial subgroup again. Now we have the internal Euler characteristic, so let's see what that comes out to. The internal Euler characteristic would usually be the Euler characteristic of the closure inside of G mod H, but now this is an entire path component, so it is already closed, it is its closure, and there's no boundary. So this is just the usual Euler characteristic of this smooth closed manifold M, which is one of the components there. Also, something else happens. In this space, G acts transitively by conjugation, by left translation, so it moves the path components around, and they're all homeomorphic. So all the path components here are actually homeomorphic, and the additivity of the Euler characteristic tells us that the Euler characteristic of any one component is simply the Euler characteristic of G mod H divided by the number of components, so by the cardinality of the set of components. So we can plug this in, and so we get the sum has the coefficient Euler characteristic of G mod H divided by the number of path components in G mod H. Okay, so this is now as a self-map from the H equivariant homotopy group of X down to the non-equivariant homotopy group of X. Now, as I said a little bit earlier, in the global situation, we can simplify this even further. If X is global, so I mean if the G action on X is trivial, then as I explained on the last whiteboard, G lower star is always the identity. So we're summing the same term as many times as we have in the denominator here, so we can just pull this out. So if X is global, we arrive as the formula restriction from G to E after transfer from H to G. It's just the Euler characteristic of G mod H multiplied by restriction from H to the trivial group. A very similar argument applies to the sort of dual case where the other subgroup is trivial. So the other special case that works out very similarly. That's the special case where H is the trivial subgroup and not G is the trivial subgroup. And then a very similar argument shows that if we restrict from G to K, after having transferred from the trivial group up to G, we get the Euler characteristic, so now of the left translation action of K divided out by G, by the number of path components that this has, by 0 of K mod G, and then sum over all connected components of G by the K action, and then now we have this in the other order. Now we have the transfer from E to G followed by G lower star. It's a very similar argument, and again, if X is global, all these conjugation homomorphisms will be identities. So if X is global, we can simplify this formula even further. If X is global, restriction from G to K after transferring from the trivial subgroup to G is just the Euler characteristic of G mod K multiplied by the transfer from the trivial subgroup to K. One more general relation. So this is the special case where we take K equals H, and this is normal end of finite index in G. So if we're assuming that H is normal in G, then we better want to assume finite index right away, because otherwise we would have this relation. Otherwise it would have infinite index in its normalizer and the transfer would be 0 anyhow. So in order to get some non-zero relation, we assume that this is finite index. And then we have the following situation. So then the double coset space, where you divide out by the two H actions. Well, after you've divided out the right H action, the left action will be trivial because H is normal. So this again is a very nice smooth closed manifold. And we will just index by the path components there. And also because it's finite index, this is just a discrete set, so we don't have this complicated thing with the internal Euler characteristic coming up. So this is finite and discrete. And then the double coset formula comes out as follows. We transfer from H to G, and then we restrict back to the same subgroup H, and then we just get a sum over GH in G mod H. Now we restrict down to K intersected with its conjugate, H intersected with its conjugate, but that's always H itself, so there's no actual restriction happening. Similarly, there's no transferring happening, so this is just the sum over all the conjugation homomorphisms indexed by this quotient G mod its normal subgroup H. So this is multiplication by what's sometimes called the norm element in the group. This is enough for general properties that we can get from the double coset formula. And now I want to move on to a very concrete example. And I'll start with a rather simple, but not completely trivial example. So here it is. I want to consider the big group to be the symmetric group on 3 elements, the group of permutations of the set 1, 2, 3. I want to take as H the alternating subgroup inside, and I want to take as K the cyclic group of order 2 generated by the transposition 1, 2. All the transpositions are conjugates, so I could also have taken any of the other ones. So what's the double cosets set going to look like? So if I divide out the action of the alternating group, I already only have 2 elements left, and those are permuted by any of the transpositions. So this has just 1 element. So there's only 1 double coset because this group and this group, if you multiply them, you get all the elements. So the double coset formula in this situation is something very simple. If I transfer from the alternating group all the way to the symmetric group, and then I restrict from the symmetric group to the group generated by this transposition, well, the smart choice of double coset representative is the identity element. That's the simplest one we could choose. So we just get the restriction from the alternating group to the intersection of these 2 groups, which is the trivial subgroup, and then we have to transfer up again from this trivial subgroup to this. Another concrete example involving the symmetric groups is the following. I take as the ambient group the symmetric group on n letters, and I take the 2 subgroups be equal, and I take them to the symmetric group sigma n minus 1, and I secretly identify this with a subgroup of sigma n of those permutations that fix the last element n. So what do the double cosets look like? So there are two of them, and sigma n has two sigma n minus 1, sigma n minus 1 double cosets. And here are some convenient representatives. I take the identity element, that's always convenient to choose it of this special double coset, and then there are lots of choices for the other one. You just have to take any element that actually does move the last number n, and I guess the one particular convenient one is to choose the transposition that interchanges n minus 1 and n, and I call this t for transposition. And then you can work out what the conjugate subgroups look like. So if I conjugate sigma n minus 1 by this element t, it doesn't matter from which side I conjugate, because this has order 2. I always get sigma n minus 2, by which I mean the subgroup of those permutations that fix the last two elements. And so the double coset formula will now have two terms. So if I transfer from sigma n minus 1 all the way up to sigma n, and then I restrict down from sigma n to sigma n minus 1 again. I first get the term which corresponds to the identity element, where I'm intersecting the group with itself, nothing happens. Conjugation by 1 is the identity, in the transfer nothing happens, so this gives me the identity operation. And then I get a second term, and this will be the restriction from sigma n minus 1 to sigma n minus 2, followed by the conjugation homomorphism by t, and then the transfer from sigma n minus 2 to sigma n minus 1. So this is a general formula that you have in a Mackey functor for the symmetric group sigma n, or in the equivariant homotopy groups of a sigma n orthogonal spectrum. But then if x is global, or if we have the algebraic object that's going to be called a global functor a little bit later, then something special happens, because then t lower star is again the identity, because this element t n minus 1 n, it centralizes the subgroup sigma n minus 2. So that's exactly an example of the situation where I said something special happens globally. If it centralizes it, you're not going to see it in a global functor. The next example will be one where you really need the full double coset formula, which will involve a concrete example of positive dimensional compact Lie groups, and it will illustrate some of the non-trivial new features that come up in that context. In the next example, I take the ambient group to be an orthogonal group. So G will be the third orthogonal group. As the subgroup H, I take the second orthogonal group, and I think of this embedded as the matrices of this form A 0, 0, 1 here. So this is how I could consider the second orthogonal group as a subgroup of the third orthogonal group. And as my K, I take the permutation subgroup, K sigma 3, embedded as permutation matrices. Okay, so now we have to work out the double coset space, and in this example we will see some of the features that come up in general. We will see these various orbit type submanifolds, and this helps us to explain the structure of the double coset formula a little bit better. So let's first look at the coset space G mod H, and there we exploit that this is a familiar space. So I can look at the map from O3 modulo O2, which would be my G mod H, and I map this to the unit sphere in R3. So these are all the vectors x, y, z in R3, such that x squared plus y squared plus z squared is 1, and the map sends a coset A times O2 to the action on this vector 0, 0, 1, Equivalently, I'm taking the last row of this orthogonal matrix A, that's going to be a unit vector. So this is a homomorphism, or even a diffeomorphism. And under this diffeomorphism, which is nice because then we can actually picture this homogeneous space, what does the K action correspond to? K equals sigma 3 action, it just becomes the coordinate permutation action. Becomes the action by coordinate permutations. So an element in the symmetric group acts on a vector x1, x2, x3. Well, since I have left actions, I need to take the inverse, sigma inverse of 1, sigma inverse of 2, sigma inverse of 3. And I guess I'm not completely consistent. I think I should always be writing column vectors that would be more consistent, but here I have written row vectors. I hope you'll forgive me for this slight inconsistency. Okay, so now we can picture this, and now we have to understand what these orbit-type manifolds are. So we have to look at the conjugacy classes of subgroups in K, which is sigma 3. So what kind of subgroups does sigma 3 have? It has 3 conjugacy classes, 4 conjugacy classes of subgroups. So let me draw them here. We have the full group sigma 3, which has 6 elements. Inside we have the alternating group with 3 elements. Then we have any of the 3 subgroups generated by the transpositions. They're all conjugates, so this is a representative of order 2. And we have the trivial subgroup. Now we have to work out what kind of stabilizers can occur and what the points with these stabilizers look like. So first of all, what are the points in the sphere with respect to coordinate permutation action which have stabilizer the full group, so the fixed points? So what are the sigma 3 fixed points? Well, there are exactly 2 of them. So all of the coordinates have to be the same. So this is plus minus 1 over square root 3, 1, 1, 1. And you want to say it's 1, 1, 1 and minus 1, minus 1, minus 1, but they wouldn't have length 1, so we have to normalize this a little bit. So there are 2 fixed points. So what are the points that have stabilizer A3, which is normal? So it would always be this. And here the observation is that if a point of S3, S2, I mean the unit sphere in R3, is fixed by the alternating group, then all 3 coordinates already have to be the same, then it's even sigma 3 fixed. Then it is fixed by sigma 3. So another way to say this is that in an earlier notation, if I look at the points which correspond to the conjugacy class of A3, which is normal, so it's the whole group, this particular example is empty. So of the 4 conjugacy classes of subgroups, this one will not come up, it will not contribute to the double coset formula. Okay, so what are the points that have stabilizer group transposition? Well, these are the points where 2 coordinates are equal, but not all 3 coordinates are equal. So S of R3, 1, 2 are the points where 2 coordinates are equal, but not all 3. And finally, for the trivial subgroup, these are the 3 points where the stabilizer group is trivial, so these are all coordinates, the points where all coordinates are different. So one of the reasons why I've chosen this particular example is that we can draw a picture of what the situation looks like, and this I will draw for you on the next whiteboard. So we're looking at an example where G mod H is the unit sphere in R3, so it's a 2-sphere, and we have the permutation by coordinates action of the symmetric group on 3 letters, so I can actually draw a picture of the situation. So here's a 2-sphere. The unit sphere in R3, as I explained a little bit earlier, we have 2 fixed points. So this is the point 1 over square root 3, 1, 1, 1. And then on the opposite side, so this is like in the back, there's the other fixed point, which is minus 1 over square root 3, 1, 1, 1. And then we have the special points whose isotropic group is a group with two elements. And these will be the points where two of the coordinates are the same. And they come in 3 great circles or 6 semicircles. So this is one of them. Then there's another one here. And another one here. So for example, I'm not telling you how exactly I've rotated the picture, but say for example, these are the points of the form x, x, z, where two coordinates are the same, and then the other great circles would be the one where, say, the first and the last coordinate are the same, or the second and the last coordinate are the same. So if you contemplate this picture a little bit, then you can actually see a fundamental domain of the sigma 3 action on the sphere. Namely, you can take 1/6 of this picture. You know, most of the points the action is free, and sigma 3 has 6 elements, so let's take one of these segments 6 here, down here, and draw it a little bit differently. So it looks like this. Here we have the fixed points, 1 square root 3, 1, 1, 1. Down here we have the other fixed point, minus 1 over square root 3, 1, 1, 1. So it's a minus here. And then here. So if we do it cleverly, then we let this be the points x, y, z, well, which are different, but we can actually choose a fundamental domain here in the real numbers after all by insisting that the first coordinate is strictly less than the second coordinate, and that's strictly less than the third coordinate. So this is kind of the interior. That's the points where the isotropic group, let me draw in green, the isotropic group is the trivial group here. Then on this side, on this end, we have points of the form x, x, z, with x strictly less than z. So here, the isotropic group is the transposition 1, 2. And then on this side, we'll have the points x, z, z, with x less than z. And here, the isotropic group is 2, 3. And of course, up here, the isotropic group is everything, sigma 3, everything. And the nice thing about this fundamental domain is that the sigma 3 action on this fundamental domain, on this 1/6 of the 2 sphere, it does not identify any 2 points anymore. So this is at the same time also a picture of the quotient space. After I divided out the sigma 3 action, there all these 6 things are getting identified, and this is a picture of the quotient space. And here you can now very nicely see the decomposition into orbit-type manifolds. So there the fixed points, this is the fixed point manifold, but it has 2 path components, so this will give us 2 summands that contribute to the double coset formula. Then the conjugacy class of the transpositions has this and this, these open intervals, and these are the 2 connected components. So again, we get 2 contributions to the double coset formula from the conjugacy class of the transpositions. And then the interior of this segment is the entire connected component that corresponds to the trivial subgroup. So altogether we get 5 contributions, 5 summands in the double coset formula. And now I will go through these 5 summands, but I will first erase the right half of the Blackboard so that I'll have a little bit more space to write something on, and then I'll be back. Before I go through the 5 summands in the double coset formula for this transfer from O to O3 and then restrict it down to the symmetric group on 3 letters, let me point out that you can also very nicely see here that in general these orbit-type submanifolds will be locally closed. You know, we have this open interval here and another open interval. This is open in its closure, but it's not neither closed nor open in the thing in general. So this is the stratification in terms of subspaces, each of which are topological manifolds. And you know, for example, here to calculate the Euler characteristic of this contribution, we have to close up in the full space, which will add these 2 points, and then subtract the Euler characteristic of those 2 points. This will come up in a second. Okay, let's calculate the 5 contributions that we get. So let's start with the fixed points. Sigma 3 fixed points. And now we have to recall, you know, we have to choose these elements that were previously called little g, such that k little gh lies in the M, in the component. So if we start with this, there's only 1 point in there, but we have to remember how this isomorphism worked. So we took the coset of a 3×3 orthogonal matrix and passed to the last row. So if we want the little g here, we have to take this will be our last row, and we have to extend it to an orthogonal matrix. So this is a choice where I don't find a particularly natural choice. So I'm not even going to write down a particular one. So choose an A plus in O3 whose last row is 1 over square root 3, 1, 1, 1. Because this will be mapped to that fixed points under this isomorphism. I call this A plus. And then for the other one, that's easy. Once you've made that choice, you just set A minus is minus A, because then its last row will exactly be this. And then what will the contributions be? Well, what are the internal Euler characteristics? Well, in this situation, we just have points. So the Euler characteristic, the internal Euler characteristic is just the Euler characteristic, so it's just 1. So the coefficient will be plus 1, and so we get 2 summons. So one summand will be, we restrict from O2 down to the intersection of sigma 3 conjugated by A plus intersected with O2. And you know, depending on which choice you take, you might want to work out what this is. And then we take the conjugation homomorphism induced by this. So in this situation, we will have the special situation that sigma 3 is already contained in the conjugate by A plus and also by A minus of O2. So that means down here, after we've conjugated, we are already in sigma 3, so we don't have to transfer up anymore. I mean, this comes from the fact that sigma 3 is the full stabilizer. So the stabilizer here is the group that in the last step we would have to transfer up from to the full group. But here and here it's already the full group, so there's no transfer necessary in front of this here. And then the other contribution, so this will be with the coefficient plus 1, the other contribution will look exactly the same, A minus, lower star composed with the restriction of O2 to sigma 3 conjugated by A minus intersected O2. And again, this, after you conjugate this, you will already have the full group sigma 3. So these are 2 of the summands. They come with coefficient plus 1. So how about these 2 contributions we get from the conjugacy classes of the transpositions? Well, what's the Euler characteristic? So this is an open interval. If we close it up in the double coset space, we get the closed interval that has Euler characteristic plus 1. And then we have to subtract the Euler characteristic of the topological boundary. This has 2 points, so we have to subtract 2. So we get internal Euler characteristic minus 1. So this example also shows that you don't necessarily get positive coefficients in the double coset formula. Generally, you might as well get negative coefficients. So these are where the stabilizer is 1, 2, or in its conjugacy class. So if we want to calculate this, so here's a nice element 0, 0, 1, which is of the form xxz with x less than z. So if we want a matrix that has this as its last row, we'll have to sort of turn it upside down. The identity matrix does the job. So this summand will be the one that corresponds to the double coset of the identity. So we take E3 as 1, 0, 0, 0, 1, 0, 0, 0, 1 as our little g. So we get no conjugation homomorphism. The conjugation is, of course, the identity. And then the summand will be minus, which is the internal Euler characteristic of this open line segment. And then we have to restrict from O2 down to the intersection of O2 and sigma 2. And this is sigma 2. Embedded as the permutation matrices in the upper left square, and then we have to transfer back up from sigma 2 to sigma 3, and this comes with a minus sign. And then we have to choose some matrix whose last row is an element in here, and here, for example, we could take -1, 0, 0, so this would be a vector which lies on this segment, and then we choose some matrix that has this as its last row. So for example, I can take the matrix B, which looks like this, 0, 0, -1, 0, 1, 0. Sorry, I want a different one. I want 1, 0, 0, 1, 0. So the last row, so the image under this homeomorphism lies in this segment. Here's a particular choice. And then again, the internal Euler characteristic is -1 because it's an open line segment whose closure is a closed interval. And so this will get us a -1 for the internal Euler characteristic, and then we'll have to transfer from this time the other transposition here to sigma 3. And now we have a conjugation homomorphism, B lower star, conjugation with this matrix, followed by restriction from O2 to sigma 2. And then there's one last term, so this comes from the interior. So let me squeeze it in down here, although this is maybe not great style, but I don't want to erase the Blackboard again. So the 3 points, these are all the points in the interior with stabilizer group E. So here's one matrix that you can take, whose last row is a point in here. I take the matrix 1 over square root 2, and then 0, square root 2, 0, 1, 0, 1, -1, 0, 1. So this is an orthogonal matrix. What's the internal Euler characteristic? So, okay, this ends here. What's the internal Euler characteristic going to be? Well, the closure of this is a 2-disk with Euler characteristic 1. The boundary is a circle with Euler characteristic 0, so we get internal Euler characteristic +1, and this will give us another contribution, transfer from the trivial group to sigma 3. That's because the stabilizer is the trivial group after the conjugation homomorphism determined by this matrix, after restriction from O2 to the trivial group. So altogether, the double coset formula for transfer from O2 to O3 and then restriction from O2 to sigma, O3 to sigma 3 has 3 terms. So this term with coefficient +1, this term with coefficient +1, this term with coefficient -1, this term with coefficient -1, and finally this term with coefficient +1. Of course, the important thing is not to remember the precise formula, but to illustrate what goes into analyzing this. And as I said before, this illustrates some of the features that can come up in the general double coset formula, and what gives you a concrete example of what such a double coset space can look like, and what the stratification that is relevant for the double coset formula can look like. So these are all the examples that I want to do on the whiteboard, but of course the best way of learning mathematics is to actually do mathematics yourself. So I'm going to suggest an exercise now that you might want to do to familiarize yourself with the double coset formula, work out what the double coset space looks like explicitly, find representatives for these m's, calculate the intersections, and write down the double coset formula. So here's the example that you might want to do. We take the ambient group as the second unitary group, U of 2. Take as the subgroup H the diagonal maximal torus, so these are the diagonal matrices with entries from the circle group U1 on the diagonal. This is the 2 torus abstractly. And as the group K, we take the maximal torus normalizer, in which the maximal torus is an index 2 subgroup, so it's generated by this diagonal maximal torus, together with the matrix which has 1, 1 off diagonal. In this example, if you do it all correctly and work it all out, you will get 3 contributions at first sight, but then you will find out that one of the transfers that comes up in one of the 3 summands is actually one where the group you're transferring from has infinite index in its normalizer. So while it first seems that you have 3 summands in the double coset formula, one of the summands is actually 0 by this infinite normalizer condition. If you don't want to do the exercise yourself, or if you want to check later if you've calculated things correctly, then there's also reference to the global homotopy theory book. So if you've seen me do a double coset formula example for you, and you might have done another example yourself, and then you will see that there are quite a lot of possibilities for making mistakes in these things. You know, you could choose wrong representatives little g, you could make a mistake when you calculate these intersections, k intersected the g conjugate of h or something like this. So I want to tell you about one checksum that you can do, which is a consistency checksum for the double coset formula. So whenever you do it, here let me write down the double coset formula one more time. Restriction g to k, transfer h to g is, well, sum over the m's that I've talked about a number of times, internal Euler characteristic, transfer k intersected gh k after g lower star after restriction from h to kg intersected h. So the following formula also always holds, and I'll call this the checksum. The Euler characteristic of g mod h, you know, which is the contribution that comes from this transfer, it has to sum up to all the contributions from the same transfers here multiplied by the respective coefficients. So this has to come out as the sum over m. So the sum is taken over the same things as in the double coset formula, first conjugacy classes of subgroups of L, and then connected components of this isotropy submanifolds, and then the internal Euler characteristic of m times the Euler characteristic of k modulo k intersected gh. So in other words, if you throw away these things, you replace that by the Euler characteristic of this homogeneous space, you sum it up with the same coefficients, you must get the Euler characteristic of g mod h out. So this is the check that I recommend doing. Of course, if this comes out correctly, it doesn't mean you haven't made a mistake somewhere else, but it's a little bit of a consistency check. So for example, in our example, how does this work? So in our example, we had g equals O3, h O2, k sigma 3. So in this situation, we had the Euler characteristic of O of 3 modulo of 2, where this was a 2 sphere. So this is the Euler characteristic of the 2-dimensional sphere, which is 2. On the other hand, we had 5 summands, and now it's gone from the board, but you can sort of look it up by rewinding. We had the 2 fixed point contributions. They came with coefficient +1, that was the internal Euler characteristic, and they were transfers which didn't really show up, transfers from sigma 3 to itself. And we had 2 of them. Then we had the 2 summands coming from the conjugacy classes of the transpositions, and there the internal Euler characteristic was -1, and we had 2 of them. So we have -1 times sigma 3 modulo 1, 2, minus the Euler characteristic of sigma 3 modulo 2, 3. And then there was the last contribution, which came from the 3 points. This again had internal Euler characteristic +1. And there were 3 points, so it's the Euler characteristic of sigma 3 modulo E. Now in this example, because our K was a finite group, these are just finite sets where you just count the Euler characteristics are just the cardinalities of these sets. You know, in general, they would also be spaces where you'd have to take the Euler characteristic. But right now, you know, first this would be 1 plus 1. Here this has index 3, so -3 minus 3, and this is 6 plus 6, and the consistency check works. You also get 2. So this is the consistency check in action in this particular example. In case you wonder what the mathematical rationale behind this checksum formula was, let me also give this away. So what's going on behind the scenes here is that there is a global Mackey functor that's usually called the constant Mackey functor with value z, the abelian group of the integers. This is also the homotopy group global functor of a certain global Eilenberg-MacLane spectrum. So this global Mackey functor is called the constant Mackey functor because its value at every compact Lie group G is always the group Z, the additive group of the integers. All the restriction homomorphisms are the identity maps, that's where the constant comes from. Of course, the transfers cannot be the identity maps then, this would not make the double coset formula work. So the transfer from H to G in that example of the constant global functor will be multiplication by the Euler characteristic. And this checksum that I wrote down on the last Blackboard is simply the double coset formula in this particular example of either a global stable homotopy type or of a global functor, global Necki functor. That's what's really mathematically going on in the background. All right, I would like to sum up now what we have learned about the structure of the equivariant homotopy groups of an orthogonal spectrum. So here's a summary. Structure of pi 0g of x for an orthogonal spectrum X. And varying compactly groups G. So, of course, we have all these values, which are abelian groups, and they are natural for homomorphisms of orthogonal spectra. So, a little while ago, I talked about the restriction homomorphisms. Alpha upper star from pi 0 g equivariant of x to pi 0 k equivariant of x for every homomorphism, every continuous homomorphism. Alpha from one compact Lie group J to another compact Lie group G. Then we have the transfer homomorphisms. Transfer from H to G, which goes from pi 0 h of x to pi 0 g of x for every closed subgroup h of g. And then these satisfy a bunch of relations. The following relations we've seen so far. Okay, so what were these? So first of all, the restriction homomorphisms are contravariantly functorial. Restriction contravariantly functorial. So transfer is covariantly functorial. Earlier I'd called this transitive, and of course the transfer from H to H is the identity. Then we've seen that inner automorphisms induce the identity. Then we discussed that transfers commute with inflations and what precisely that means. This is just a slogan. Finally, we saw that the transfer sometimes vanishes, namely whenever H has infinite index in its normalizer, whenever H has infinite index in the normalizer Hg, or equivalently if this normalizer has a strictly larger dimension, and then finally the double coset formula holds. And I'm not going to write that down. Again, you've seen it often enough now. So various things you said earlier suggest that this is somehow the full natural structure that we have on equivariant homotopy groups. Well, they are. Yeah, but how can we show this? Shouldn't we rigorously be showing that in the next lecture you don't come up with yet another operation or with another relation that sort of we haven't seen yet? Okay, that's a good point. So we should somehow be rigorously proving that we have found all the natural operations and that we have also found enough relations that generate all the relations. I will actually give you a precise statement which makes this rigorous, that these are all the operations and all the relations. And this will involve something that I'll call the global Burnside category. Proving that these are all the operations and relations will take us quite some time, and that I will not be able to do anymore today, but at least I want to give you this statement now. I package all the natural operations between the equivariant homotopy groups into a category that I call the global Burnside category. So the global Burnside category that I denote by A. So in the writings, this is a bold A, but now here it's just a straight A. So has as objects all compact Lie groups. And as morphisms, the following sets: A, G, K. The morphisms in the Burnside category from G to K. It's just a set of natural transformations of functors from orthogonal spectra to sets, from the equivariant homotopy group functor pi 0 G to the equivariant homotopy group functor K. So some comments are in order here. So pi 0 G and pi 0 K, the equivariant homotopy group functors, they are functors on the category of orthogonal spectra to the category of sets, so we can consider the set of all natural transformations between these functors. On the face of it, you might wonder whether this is really a set or just a class, whether it's too large. Well, at some later point we will show that the functor pi 0 G is representable, and then the Untitled lemma will imply that this is actually a set, so you don't have to worry about this. So this is a category. Obviously, under composition you can compose natural transformations, but this is also a pre-additive category, so it has a little bit more structure. This is a pre-additive category by pointwise addition of transformations. So while I'm considering natural transformations of set-valued functors, this is actually a homotopy group and a abelian group, so we can pointwise add natural transformations. This gives us a new natural transformation. Pre-additive category means that on the Hom sets we have abelian group structures and composition is bi-additive. And this of course needs a proof now, and the point here is that because these two functors, pi 0 G and pi 0 K, are additive functors, they take wedges of orthogonal spectra to direct sums of abelian groups. The consequence of this is that set-valued natural transformations are actually already additive transformations, and that really means that composition is additive in each variable. So this is a wonderful category that makes precise what we mean by the collection of all natural transformations. And now the main result is that this is actually calculable, and here's the main theorem that we will eventually prove, so that G and K be compact Lie groups. Then this morphism group, A, G, K, is a free abelian group. With a basis that we can pin down, with basis given by the following operations. Transfer from L to K after alpha upper star for all pairs L alpha, consisting of, first of all, a closed subgroup L of K with finite Weyl group. So L is assumed to have finite index in its normalizer. The normalizer has the same dimension as L. Otherwise, this operation would be trivial and we wouldn't need it. And alpha is a continuous homomorphism from L to G. So if we have this data, we get a natural transformation from pi 0 G to pi 0 K, first restriction, then transfer. But we don't actually run through all of these pairs, but only up to K times G conjugacy classes of pairs. Up to K times G conjugacy. I will make this more precise next time. So simultaneous conjugation of the subgroup and the homomorphism. And then if we pick representatives of these conjugacy classes, then we actually get a basis of this. So every natural transformation is uniquely a finite Z linear combination of these operations as long as we take K times G conjugacy classes. This is the first major result. This is really truly of a global nature, and it needs quite some kind of different inputs. It will take us more than one lecture to prove. And this is a wonderful point to stop today's lecture and to thank you for your attention.